Alright, so in this video we will finish our notes on the gamma function. So in the last lecture we were finding the gamma function of uh, odd multiples of a half or negative odd multiples of a half. So let's briefly recap what we did using the definition of gamma of n plus 1 equals to n gamma of n. So we found gamma of 3 halves, 5 halves, 7 halves, and on the negative counterpart we found gamma of negative a half, gamma of negative 3 halves, and gamma of negative 5 halves. But what if we wanted to evaluate, say, gamma of 13 halves or negative 13 halves? Well, this process of evaluating uh, or using the definition of gamma function backwards and like we did in the last couple of examples would be very inefficient to do. So we're going to look at the last formulas from the notes right here whenever we wanted to evaluate gamma of a number plus a half or negative a number plus a half where the number is actually an integer. What do? We will multiply all the odd multiples of all the odd integers rather up until 2n minus 1 which is the number that appears in the inside of the parentheses, or we have another formula right here that you of course are not required to memorize. All right, well, so in a similar way we have one for a negative n plus a half, which it's number one, it's flipped upside down, but there's a negative 2 raised to the n as opposed to the 2 to the n in the previous example. So I'm going to show you how we get these results later. In the meantime, well, let's apply this to finding gamma of 19 halves. Well, that's kind of a big number. So the number one thing you want to do is identify or rewrite, first of all, gamma of 18 plus 1 divided by 2, and that equals to gamma of 9 plus 1 half. Right? So here n equals to 9, and 2n minus 1 equals 2 times 9 minus 1, which equals 17. Why are we computing the 2n plus 1 quantity? Because this is going to tell us what to do when to multiply, or how many integers are we going to multiply. That is, we're going to multiply all the, well, not all the integers, all the odd integers, 1, 3, 5, 7, 9, all the way up to 17. So this will be 1 times 3 times 5 times 7 times 9 times 11 times 13 times 15 times 17 over 2 to the 2 to the end, which is 2 to the 9th power, that is times the square root of pi. All right, well, so although we could leave the result like this, I mean, try to compute the numbers, that's going to give us a really big number. We can write these numbers in a more compressed way using factorials. Actually, what I'm going to do next, it's going to be related to the other form of computing the gamma of a bigger multiple, odd multiple of a half. Well, so how do we do this? Well, let me copy this. Let me copy this quantity again. Let me copy and paste, and I'm gonna leave some big space before that expression. So I mean that means that's good here. All right. Okay. So what about the product of integers in the numerator? Well, that looks a lot like the factorial, but it is not a factorial. We can make it look like a factorial if we had the 2 right here, the 4, the 6, the 8, etc. We don't have them, but we can multiply by those numbers. So this is what's gonna happen later. Okay, so let me write it down. So I'm gonna multiply all the integers, 2 times 4 times all the missing integers up to 16 times 6 times 8 times 10 times 12 times 14, and I need some space for the 16. Okay, times 16. And then we're going to divide this by the same number, because if we multiply by one quantity, we divide by the same quantity. 2 times 4 times 6 times 8 times 10 times 12 times 14 times 16. Okay, so if we group all this, what do we have? 1 times 2 times 3 times 4 times 5 times 6 times 7 times etc. all the way to 17. So this will be equal to 17 factorial in the numerator. Okay, what about the denominator? Okay, do you guys agree that this is it's a product of even numbers? That is, every single number in the denominator has a factor of 2. All right, that is, this is let me write it with different color instead. Okay, so this 2 is the same as saying 2 times 1. This 4 is the same as saying 2 times 2. This 6 is the same as saying 2 times 3. This 8 is the same as saying 2 times 4. Then 2 times 5. 2 times 6. 2 times 7. 2 times 8. All right? It's 2 times 8. Well, how many factors of 2 do we have here? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is the same as saying 2 to the 8, right? And we are left with the numbers 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. Isn't that 8 factorial? So that is 2 to the 8 times 8 factorial. All right, so let's go back to the original number right here. So I'm going to write this quantity in green that I wrote in yellow as 2 to the 8 times 8 factorial. And then don't forget this 2 to the 9. That's 2 to the 9, which is times square root of pi. All right. So combining the powers of 2, that'll leave us with, well, 17 factorial in the numerator. And then this will be 2 to the 17 times 8 factorial, square root of pi rather. All right, so that'll be the result of the gamma of 19 halves. All right, well, so this is how we get the second form of this formula. That is 2n minus 1 factorial, which is 17 factorial, divided by 2 raised to the 17, which is the 2 raised to the 2n minus 1, and then 8 factorial, that comes from n, which is 9 minus 1 factorial. All right, so you can easily do this quicker with this form instead. All right, and lastly, I'm going to do one with a negative number, but I'm going to go straight to use the second form. Rather than writing the whole product, I'm going to use this form right here. All right, well, so number one, let's write negative 15 halves that as a gamma of what is that? Negative 16 plus 1 over 2 equals to negative 16 over 2. That's gamma of negative 8 plus 1 half. All right, in this case, what's n? N equals to 8, and 2n minus 1 equals 2 times 8 minus 1, which equals 16 minus 1, which is 15. And again, I'm going to go straight to the formula rather than the crazy product. Okay, so in this case, well, the formula would be negative 1 to the n, which is negative 1 to the 8, times 2 to the 2n, which is 8 minus 1, times n minus 1 factorial, which is 8 minus 1 factorial, divided by 2n minus 1 factorial, which is 2 times 8 minus 1 factorial, square root of pi. All right, so that is negative 1 to the 8th power becomes a positive result. And then what do we have? 2 times 8 equals 16 minus 1. That's 2 to the 15. X minus 1, that's 7 factorial over 15 factorial square root of pi, right? So we may not be evaluating the gamma function of a number this big or this crazy, but just in case we were in the need, we can simply express it like this. You don't have to evaluate this in the calculator because you may have an overflow issue with the graphing calculator, so we can simply leave it like this, right? And this actually concludes the notes for the gamma function.